All right, today we are going to crack open a really classic physics problem. Our mission is to investigate a special type of force to figure out what a potential force actually is, and, more importantly, why knowing how to spot one is basically a superpower in physics. So we're tackling problem 1.133 from Irodov's Problems in General Physics. Now, if you've been in physics for a while, you've probably heard whispers about this book. It's famous, or maybe, a little infamous, for problems that really make you think. And this one, it's a perfect example. So the problem asks us to figure out if these two force fields are potential. But hold on, before we jump into the math, what does that word even mean? It's a really fundamental idea that separates forces like gravity from other forces like, say, friction. Okay, here they are, our two suspects. We've got two force fields described by these two little equations. So let's put on our detective hats. Our job is to investigate each one and determine if it's a potential field. This whole investigation, it all comes down to one single major clue, and that clue is an idea called path independence. This is the defining feature of a potential force field. So what is path independence? Well, simply put, it means the work done by the force only cares about your start point A and your end point B. The actual route you take to get there doesn't matter one bit. You can take the long, scenic route or the direct shortcut. A potential force just doesn't care. The best way to picture this is to think about climbing a mountain. It doesn't matter if you scramble straight up a really steep cliff or if you take that long, winding trail that zigzags all the way to the top. Your change in gravitational potential energy is exactly the same. All that matters is where you started and where you ended up. And that's because gravity, yep, it's a potential force. Okay, so we get the concept. But, in practice, how do we test this? We can't sit here all day checking every single possible path from A to B. That would literally take forever. So as good detectives, we need a tool, right? A reliable test that tells us for sure if a force is potential. And thankfully, calculus gives us this beautiful, elegant shortcut. It's just a simple three-step test. First, you break the force down into its x and y parts. Second, you calculate these two very specific partial derivatives. And third, you just check if they're equal. If they are, boom, the force is potential. Case closed. Now listen up, because this is super important. This is a classic spot where students mess up. You have to notice the cross-check in this test. You take the derivative of the y component, but with respect to x, and you take the derivative of the x component, but with respect to y. You gotta get that crisscross right, or the whole thing falls apart. All right, let's do it. Time to put our first suspect, the force field F equals AI, to the test. Okay, step one, what are the components? Well, that little I is just a unit vector. It's telling us this part of the force is in the x direction. So our x component, F sub x, is A. Now, you might be looking for a j vector for the y direction, but there isn't one, is there? So that means our y component, F sub y, is just 0. Now for step two, the derivatives. And remember that cross-check. So we take the y component, which is 0, and we find its derivative with respect to x. Well, the derivative of a constant is always 0, so that's easy. Then we take the x component, ay, and find its partial derivative with respect to y. That just means we're asking how a changes as only y changes. In that case, we treat a as a constant, and the derivative of y with respect to y is just 1. So our result is a. And that brings us to the final step, the moment of truth. Are these two results equal? Is 0 equal to a? Well, the verdict is in. The problem specifically says a is a non-zero constant. So no, 0 does not equal a. The test fails. Our first suspect, F equals AYI, is definitely not a potential field. All right, one down, one to go. Let's bring in our second suspect for interrogation, F equals XI plus BYJ. Step one again. The x component is just the part with the I, so that's AX, and the y component is the part with the J, so that's BY. Pretty straightforward, right? Okay, time for the cross-check derivatives. First, the derivative of the y component, by, with respect to x. Since there's no x in by, we just treat the whole thing as a constant, and the derivative is 0. Now for the other one, the derivative of the x component, ax, with respect to y. Again, there's no y in that term, so we treat ax as a constant, and its derivative is also 0. So here we are again at our final question. Are the results equal? Is 0 equal to 0? Yes, of course it is. The results match perfectly. Our second suspect, F equals AX plus BYJ, passes the test with flying colors. It is a potential force field. So, we did it. We solved the problem. We figured out which force was potential and which one wasn't. But this leads to the biggest question of all. So what? I mean, why do we even care? Why does any of this matter? Here's a quick summary of our whole investigation. For that first field, our test failed. For the second one, it was a perfect match, a clear verdict in both cases. And here's the real payoff. This is why it's so incredibly important. Potential forces are also called conservative forces because they conserve mechanical energy. And that is a huge deal. It means that anytime you can identify a potential force, you get to unlock and use one of the most powerful laws in all of physics, the law of conservation of energy. It lets you take these incredibly complicated problems and just solve them by comparing the energy at the start to the energy at the end, completely ignoring all the messy stuff that happens in between. So, I'll leave you with a little something to think about. What about the force of friction? Think about pushing a heavy box across a room from point A to point B. If you take a short, direct path versus a long, winding path, do you do the same amount of work against friction? Based on everything we've just learned, what does that tell you about whether friction is a potential force? Thanks for diving into this with me.